Welcome back, everybody. And we've got one more here. I don't know what's going on with my light again. All right, there it is. Okay, just a quick announcement. Don't forget, Tuesday, exam number 4, chapters 10 through 12. Okay, again, I will be here. Obviously, if there's no questions concerning the chapters 10 and 12 on Tuesday, I'll continue with the next chapter. This chapter is pretty short, so we'll finish it up, probably finish up a little bit early. And then 14, another fairly short chapter, but we're getting to the point now that we are probably toward the end of the semester, have a lot of call it study days. So I will be here. You know, it's a good opportunity to come in and ask any questions. We can go over them. Okay, so on and so forth. So keep that in mind. All right, any questions before I begin? All right, well, let us continue with chapter 13. Okay, now this deals with stoichiometry, which is basically nothing more than dealing with the ratios that we have been working with respect to balancing these chemical reactions. For example, let's say I have a hypothetical equation here where I got A plus B reacting to give us a little bit of C and some D. And then for argument's sake, say that it takes 2 A's for 3 B's to give me, say, 1 C and maybe 4 D's, okay? So recall that exercise we went through where we were balancing these chemical equations and we put in coefficients. And we talked about, all right, now keep in mind that those coefficients, now we're dealing with the ratio of, let's say, the interaction between A and B, which says that I need 2 A's for every 3 B to react properly to give me 1 C. If there's no number in front of the chemical, it's understood to be 1, and to give us 4 D's. That relationship, these coefficients, is what this whole stoichiometry is all about, okay? And so that's what we're going to work with. So it's crucial that once we get a chemical reaction, that we balance it properly, because that coefficients from the balanced chemical equation will allow us to do calculations. Okay, we introduced the mole already to explain, you know, the common factor between reactants is we can't go from grams to grams to compare X grams of A with X grams of B, but we need a common factor, and that common factor happens to be the mole. Okay, and so we're going to expand what we've been dealing with the mole into this here, this chapter. So for example, if we have a reaction like as follows, where we have 2 nitrogen monoxides reacting with 1 oxygen, we result in obtaining 2 nitrogen dioxide. Okay. Now we've been talking about, all right, I need 2. Let me change my color here for a second. I need 2 molecules of A and nitrogen monoxide to react with 1 molecule of oxygen gas to give us 2 molecules of nitrogen dioxide, okay? And that is our ratio. That comes from the balanced chemical reaction. Well, we can also say that if I have 10 molecules of NO, I need 5 molecules for it to react properly in the correct ratio, because the ratio of, let's say, 2/1 isn't that the same thing of 10/5, okay? all we did was just change the magnitude of that ratio. And it's the same thing if I said 1/2, 5/2, they represent the same ratio. Now, we don't normally talk about one molecule, two molecules, whatever. We talk about the mole. And so in reality, we should say, rather than molecules, we can say that 2 moles of nitrogen monoxide react with 1 mole of oxygen to give us 2 moles of nitrogen dioxide. Keep in mind, this is 2 times twice Avogadro's number with respect to actual molecules. Okay, and this is 6.02 times 10 to the 23rd. Okay, 2 times that, and then 2 times 6.02 times 10 to the 23rd. So if you wanted to talk about the actual number of molecules involved, we can convert that to Avogadro's number. But, those are humongous numbers. So that's our ratio, 2 to 1. Now, the other aspect about this is as follows. With respect to this reaction, we have a ratio of 2n, and we're going to compare simply the reactants. It takes 2 nitrogen monoxides per every 1 oxygen. We can write it in that manner, or we can write it by inverting it. 1 oxygen over 1 NO. Like any conversion factor we have done, which I've explained that we can write it as a ratio. We can do the same thing with respect to the mole ratio of a chemical reaction. And we're going to utilize this quite a bit when it comes to calculations of reactions, okay? By keeping track of our units, we can determine which one of these, left or right, are we going to use. Now, if we look at nitrogen in the presence of hydrogen to give you ammonia, notice I gave it to you in a sentence, because it could be given to you in a sentence. We've had some already where a reaction was described in a sentence, and we have to take that information and convert it into a chemical reaction. And then from there, we balanced it, okay? And so here it says nitrogen, N2, plus 3 hydrogen, 3 molecules of hydrogen react to give us 2 molecules of ammonia. Replace molecules with the term moles. Again, we have 1 mole of nitrogen requires 3 moles of hydrogen to give us 2 moles of ammonia. And if you look at it, it's simply like this. Here's a molecule of nitrogen, just 1. And then we have hydrogen. We got 3 of them. Okay. And then we have 2 ammonias. So that is what you see, but instead of having to write it all out, we put the coefficients, okay? All right. Coefficients are the mole ratios to give us that how many, we generally don't talk about molecules. We're using it here to explain the concept. But generally we talk about moles. 1 mole of this, 2 moles of that, et cetera, okay? Now, how are we going to utilize this to do actual calculations? Okay. Now, prior to this, we worked on the previous one, we introduced moles and how we can use it to convert from grams to moles and moles to grams, for example, okay? Or moles to liters of some gas when we're at STP. Okay, so now we're going to actually start talking about, first we're going to talk about moles, but then we're going to convert. The next logical step is to talk about grams. So let's break it down first before we go further. Here we have this reaction of iron 3 oxide. It reacts in the presence of carbon monoxide, okay, to give us iron, the element of iron, and carbon dioxide. Notice the ratio between the iron 3 oxide and the carbon monoxide is a 1:3. So we can write it in this ratio, 1 mole of iron 3 oxide over 3 moles of carbon monoxide, or we can write it with the carbon monoxide in the numerator, okay? Also, so this is comparing the two reactants with each other, okay? But we can also look at reactants with products. So if the next scenario here, you have carbon monoxide and its relationship with iron, which is a 2:3 ratio. We can write that with CO on top and 2 irons in the denominator, okay? And that's one relationship. And then the other relationship is carbon monoxide with carbon dioxide. And then, of course, we have the iron 3 oxide, its relationship with the iron, okay? And the iron 3 oxide, its relationship with the carbon dioxide. So in essence, we have 1, 2, 3, 4, 5 different relationships. And then plus, we have the relationship of product to each other. So we have 6 relationships or mole ratios to work with, each one having 2 ratios. So that's a total of 12 ratios that we can generate based on this equation here, okay? And when we write that reaction, we put it down, then we balance it out, then we make note of that ratio because we may require one of these ratios to do some calculations, and as if they have it here in question number 1. So let's clear this up. So you have an equation, and now you're asked the question, how many moles of iron, okay, identify what you're looking for, can be formed from 10.2 moles of carbon monoxide. So when we look at the balanced chemical equation and based on the question, our only concern is the moles of iron from 10.2 moles of carbon monoxide. And so our only concern is the relationship between carbon monoxide and iron. We don't care about all the other guys, okay? And I can't overemphasize that. Sometimes I get a relationship with carbon dioxide and iron and I don't know, any number of combinations. And the question didn't even ask that. The question is simply talking about the moles of iron right here with respect to the moles of carbon monoxide right here. And that's all we care about is those 2 individuals. The other individuals, sufficient amount of reactant to react, sufficient amount of iron 2 oxide to be in there, okay? So what do? We do what we've been doing with any other problem. We write down what we're given. We're given 10.2 moles of carbon monoxide, okay? Obviously, we're gonna have a conversion factor and we're looking for moles of iron. Okay, so we need iron in the numerator, right? And carbon monoxide in the denominator because we want CO or cancel, leaving us with iron. And so now we look at the mole ratio of iron, which was a 2 in front of it, and carbon monoxide is a 3, okay? So therefore, 2/3 of the 10.3 would equal the number of moles of iron necessary for this reaction. Okay. Okay, so it requires 6.08 moles of iron are created if you start off with 10.2 moles of carbon monoxide. And the key part is this relationship here. So this number, 10.2, that can be any number you want in the world. It could be 1, it could be whatever number. This is going to vary, okay? But the mole ratio is not going to vary. It's going to be a 2 to 3 ratio all the time. Okay. All right, let's look at the next problem. And the problem is a little bit different. We got how many moles of iron 3 oxide? How many moles? We're looking for that. So we're talking about iron 3 oxide are needed to form 17 moles of carbon dioxide. And so carbon dioxide, we need to make 17 moles here. Okay, so our relationship is simply between carbon dioxide and iron 3 oxide. That's it. We don't care about the relationships of the other species, just those two. Okay. Again, we write down what we are given, which is 17 moles of carbon dioxide. Okay. We know we have a conversion factor, and we're looking for moles of iron 3 oxide. Okay. So obviously iron 3 oxide is in the numerator and carbon dioxide is in the denominator. The ratio is 1 for the iron 3 oxide and 3 for the carbon dioxide. So therefore, if you want to make 17 moles of carbon dioxide, you're going to need a third of that 17, which corresponds to as follows: 5.7 moles of iron 3 oxide are needed to begin with. Okay. Now, right now we're working with just moles, but it's a simple next step forward to go to grams, because you recall molar mass, atomic mass has the units of grams per mole, okay, or moles per gram, depending on which one I need to use. And so working with moles, the next logical step is to actually calculate grams, because when you're in the lab, you don't have a balance that measures in moles, you have a balance that measures in grams. And so therefore you need to be able to take this information and convert it to grams. And if we're looking for compounds, then recall how we did that. We added up all the atoms involved in that structure and their atomic weights for each and every one. We tallied it up, and that gave us the molar mass, okay, for that compound. Okay. All right, let's do one more. Okay, we first got to balance it, so we need 2 sulfur dioxides plus 1 oxygen reacts to give us 2 sulfur trioxide. All right, so first question, how many moles of sulfur trioxide? So we're looking at sulfur trioxide. Will form if you have 0.165 of oxygen. So if I have 0.165 moles of oxygen, okay, how many moles of sulfur trioxide are going to make? So our relationship is simply between these two, not about sulfur dioxide. So as always, notice the number is pretty small. We've been using fairly hefty numbers, but now we are reducing the moles into a smaller number, okay? And even smaller down in here. Makes a little difference. It's okay. Whether we start off with 0.165 moles or we start off with 1.6 million moles, it's the same thing with respect to the mathematical calculations. So we write down what we're given, 0.165 moles of O2. Okay, we're going to use the conversion factor here, mole ratio, I should say. And we're looking for moles of sulfur trioxide. Okay? So obviously sulfur trioxide is the denominator, oxygen's in the, denominator for oxygen, numerator for SO3. Okay. We look at the balanced chemical equation, 2, and then for oxygen over 1. Okay, so now units cancel. We are left with moles of sulfur trioxide. And notice this, look, hopefully you can pick up on this. We start off with moles of oxygen, and we're being asked to now convert that to moles of some other reactant, which is sulfur trioxide in this case. Okay, so in other words, to get from oxygen to moles of something else, we need that conversion factor. Okay, that ratio from the balanced chemical equation, that is going to get us from moles of one reactant to or product to moles of another reactant and or product. Okay, the common factor is moles. All right, so the next question, let's clear that up. Put that in here, and you can see here that moles of O2 cancel, moles right there, leaving us with moles of sulfur trioxide. So therefore, if I start off at 0.165 moles of oxygen, I'm going to make twice that amount with respect to sulfur trioxide, okay, 0.330. Now we're being asked to how many moles of sulfur dioxide. So we're looking about sulfur dioxide to make 0.043 moles of sulfur trioxide. So now we're looking at that relationship. Okay, so how many moles of that we need to make 0.042 moles of sulfur trioxide. And this type of exercise is true whether we're working with quantities in the lab or whether we're working with quantities in a large production plant. That ratio is still the same. Obviously, the difference is in the lab, you're working with grams. In the production plant, you're probably doing it with tons or at least metric tons of material, okay? But that ratio remains constant, it's the same thing. All right, so here we have it. How many moles of sulfur dioxide are needed to make 0.042 moles of sulfur trioxide. So we're going from here to here, okay? Notice the ratio is 2 to 2, which at this time, go ahead and put the 2 there until you're comfortable with it, but you can also notice that the 2's cancel, and so this amount will be the same. Obviously, what changes is the units, which in this case would be sulfur dioxide. All right. So we're going to have another flow chart here, but this is in addition to the flow chart we gave you earlier when we were talking about STP. We're going to combine the two here in a second. The point of this flow chart is to tell you this, is one, if you're now given a amount in grams of some chemical compound, we need to convert it to moles. And so I can't go directly from grams to grams. I can't go directly if I'm comparing A to B. I need to go through moles. Okay. And so from grams, I go to moles. And then from there, I get to moles of B. And then from there, I get to grams of B. Okay. And that's how you work the problem. So if you're given something in grams, obviously, you need to convert that to moles. And the way you do that is you need to know the molar mass / atomic weight, if this happens to be an atom, okay? Or the molar mass, I should say, / atomic weight if it's an atom. So we need the molar mass of the compound. With the molar mass, then that gives us the number of moles. Given is what we're given in the word problem. Then, based on the balanced chemical equation, we got the mole ratio, then will relate us to the moles of what we're looking for, what we're trying to find. And knowing what its molar mass, guess what? Now we got the grams of what we're being asked to determine. We cannot go like this directly. Okay, cannot do that. Grams to grams. You have to go through moles. So in essence, what this represents are three conversion factors. The first one is molar mass, or G given. Then we got the mole ratio in the middle from the balanced chemical equation. And then the last, we got the molar mass of F for fine. Okay, so we're going to have at least at the minimum three ratios to convert from grams of one reactant to grams of whatever we're looking for. Okay, let's take a look at this reaction. We have iron 2 oxide reacting with aluminum to give us iron and aluminum oxide. Now, can anybody tell me what type of reaction that is? What do you think? This is a typical good test question. Now look what happens to aluminum. The aluminum in that state is reacting. Is it in a compound form or ionic form? Aluminum.
I'm sorry, were you asking for what type of reaction?
Yeah, what type of reaction this whole thing is? What would you call it?
A single replacement?
Very good. That's correct. Because you notice here that the iron, we're talking two metals here. One's in ionic form. Where is my? Yeah, there it is. One's in ionic form, and the other metal is in an element. It's elemental form. And what happens is the iron that was in ionic form now gets converted back to elemental form. And then the aluminum, which was in elemental form, now is in ionic. And that represents a single replacement reaction. Very good. So we have here a balanced chemical reaction where we have iron 2, oxide reacting with aluminum to give us the iron metal and aluminum oxide. Aluminum oxide is an abrasive. You find it in a number of things. One of them is like sandpaper, light aluminum oxide in that. All right, so now you could be asked questions. I could have said this, the equation is given to you, but it could have been said in words, and it could have been said as something as follows. Iron 2 oxide in the presence of aluminum produces iron and aluminum oxide. So taking that word, that sentence, you would then convert it to the chemical reaction, and that is what you would come up with: FeO plus Al plus Fe plus Al2O3. Then you would balance it, okay? And once you got it balanced, then you check out figure out the physical states, and everything here is in solid, because there's no mention here about an aqueous solution of sorts, and most everything here is a solid. Not most, everything is a solid. Okay, so let's go. Now we got that out of the way. The next question will be, let's do some calculations. All right, so in fact, there's two calculations. In the next page, we're going to run through it. First one says, calculate the mass of iron 2 oxide needed to react completely with 5.5 grams of aluminum. Okay, now, first things first, we are looking for identify who's reacting with who, okay? And they're asking, calculate the mass of iron 2 oxide. All right, so iron 2 oxide is as follows. Question here is, how many grams, okay, are needed to react completely with 5.5 grams of aluminum. And so our only concern here is the relationship between aluminum and aluminum oxide. We don't care about what's going on with the other species in this reaction. And so our relationship here is 2 aluminum to 1 aluminum oxide. That's our mole ratio. Okay. So we identified the first who's reacting with who. So what do? Well, guess what? We first write down and we're going to go through this, but we write down what we're given and write down where we got to go, what we're looking for. Okay, so that kind of shows you what direction you need to set your stuff up for. All right, now the next one says calculate the mass of aluminum oxide. Okay. Whoa, I did something wrong, incorrect. Let me, hey, cancel what I just stated. I jumped ahead of myself. I'm reading 2 things at the same time. Let's back up, rewind, back up real quick. Okay, my apologies. I jumped ahead of myself. I don't know why anyone didn't pick up. Did anybody see where I made my mistake? Let's see if you're paying attention. Where did I mess up? Hey, good. You didn't see my mess up. We'll start again. All right, let's go back. Calculate. Let me back it up so we're not looking at the second question here. Okay, let's leave it at that. Calculate the mass of iron 2 oxide, which is this guy, needed to react completely with 5.5 grams of aluminum. So our interaction is between these 2. Okay, we don't really care about what's going on there, what's going on there. We're only concerned about what the problem. So we need to calculate the mass. So grams of iron 2 oxide needed to react with 5.5 grams of aluminum. So another way to look at this is if I weigh out 5.5 grams of aluminum, how many grams of iron 2 oxide do I need so this reaction goes as written? Okay, I got to weigh out a certain amount. So that is the first scenario. Let's go to the second scenario. Here it says calculate the mass of aluminum oxide, which is right here. We need to know the number of grams of aluminum oxide produced when 10.25 grams of aluminum react. And again, everything else we don't worry about because it's assumed there's sufficient amount of quantity for that process to work. Okay, so we're only concerned about what the question is asking us to calculate and not the other species. And I state that because I've had answers where, like here, we're asking for aluminum oxide and aluminum, and somehow iron gets in the calculation. And occasionally, I've had iron 2 oxide and iron interacting in the calculation, and I'm like, no, that's not what the question asked. All right. Okay, so let's clear it up, and now let's actually run through it. So here's the first one. Okay, our relationship is only between the iron 2 oxide and aluminum, denoted by the double arrow there. Okay, we don't care about everybody else. And so we have grams of aluminum. I cannot go directly to grams of iron 2 oxide. I have to go through the common unit, which is moles. Okay, so in order to convert grams of aluminum to moles, I need the atomic weight. The atomic weight of aluminum is 26.98. Where did I get that? From the periodic table. Okay. Check out as you set that up, look at your your units, they're canceling out like you want them. You want now at this stage, when we stop the calculation, we will have moles of aluminum, but we're not. We need to go to grams of iron two oxide. Now I rely on the stoichiometric relationship from the balanced chemical reaction between the iron two oxide and aluminum, and that ratio is 3:2. Okay. Again, that comes from the balanced chemical reaction. And if, for example, you don't have a balance, then you can see very quickly that your number would be completely way off, okay? Instead of 3/2 factor, and you went 1:1, well, that wouldn't be correct. So at this point, notice I'm checking my units. I will be, now I've gone from grams of aluminum, now I am back now to where I need to be, where is moles of iron two oxide. So see how I related apples to oranges? I started with apples. I need to find out what that corresponds in oranges. And I used the common factor of fruit, okay? And that's basically what we're doing here, because aluminum and iron two oxide are completely different compounds, okay? But I'm able to relate the quantity of each other because of the unit of mole and the balanced chemical reaction. Now we're at moles of iron two oxide, but the question has to be grams. So I need one more factor, which would be the molar mass of iron two oxide. And that's simply the sum of the atomic weight of iron and oxygen to give us 71.85 grams per mole. Remember, atomic weight or molar mass have the units of grams per mole. Now, my moles of iron two oxide cancel, leaving me with units of grams of iron two oxide, which is what the question asks to do. Okay. And now you plug in the numbers and keep track of your sig figs. Now remember, with respect to sig figs, all of these conversion factors have no factor in sig figs, okay? Atomic weights and that the mole ratio are whole numbers. They're exact numbers, no factor in sig figs. Atomic weights are the average of whole numbers. The weighted average of whole numbers would not be used for sig fig calculation. So all you can go by is what you're given, which is 3 sig figs on 5.55. So our answer is 22.8 grams. Okay, so to put this in perspective now, if I start off with 5.5 grams of aluminum, I require 22.2 grams, okay, of aluminum oxide in order for this reaction to proceed as written and to go to completion. Now, what do I mean by completion? Okay, because any number greater than 22.2 will result in an excess amount of iron two oxide. Okay, because only 22.2 grams of iron two oxide will react with 5.5 grams of aluminum. So anything greater gives you a little bit extra. You would have an excess amount of iron two oxide. If I use anything less, then I'll be making less of the final products, okay? Because I need exactly 22.2 grams of iron two oxide to get all of the 5.5 grams of aluminum to react. You might say, well, I'm still having a challenge with that. All right, let's look at it this way. I'm going to go to my bicycles for my bicycle analogy for an example, okay? So this is my crude picture of a bicycle frame. All right, don't shoot the artist. That's my frame. So you sit up here and, you know, blah, blah, blah. So I got a frame, no tires, right? Well, if this represents my tires, 2 of them. Obviously, I need 2 tires for every bicycle frame. So when I put them together and assemble the bicycle frame, I will have a fully assembled bicycle frame with tires. Okay, and so my mole ratio here is a 1:2. So let's say, for example, I have 100 frames, okay, and I have 200 tires. How many assembled bicycles would I end up with? I got 100 frames, 200 tires. Erase that, not 2,000, 200 tires. How many assembled bikes do I have? Wouldn't I have 100 assembled bikes? Yeah. Assembled, right? Now, that means I need 100, exactly 100 and exactly 200. But if I have 100 frames and I have 300 tires, well, how many assembled bikes would I have? Got 100 frames, 300 tires. How many, I'm assembling the bikes, how many would I have? How many assembled bikes would I have? Would I also have 100 again? I will have 0 frames done because all the frames were used, and I will have 100 tires left over because of those 300, 200 were used to make the frame, make the assembled bike. So I end up with 100 assembled bikes and 100 excess tires. And so here, the tires determined had nothing to do with how many I actually make at the end of the day. The frames did, because that was my limiting factor. But what if I only had 100? What if I had 100 frames and only 100 tires? Any idea how many bikes I could assemble? Okay, I'm gonna put it up here. I got 100 frames, 100 tires. How many frames would I make? Assembled bikes would I have? Wouldn't I just have 50? Right? I would have 50 assembled bikes, and then I would have 50 leftover frames. So in that case, the tires determine how many products I have, okay? And that's what's happening here with these calculations, that if I weigh out less than 22.2 grams of iron 3 oxide, I'm gonna have a different amount of final product. Okay. I can see that one's clear as mud. All right, we'll digest that a little bit, and then you have any questions about it, we'll do some more examples. All right, the next part of the question. We are starting with 10.25 grams of aluminum. In this scenario, our only concern is the aluminum, which is 10.25 grams, and the aluminum oxide. We need to calculate how much aluminum oxide am I going to make, okay? So like the first example, I need to convert aluminum to moles. So I have my atomic weight that gets me into moles of aluminum. Next one is my relationship, stoichiometric relationship, or the mole ratio of the balanced chemical equation. There's one, that is a 1:2 ratio, 1 aluminum oxide to 2 aluminums. At this point, if you're keeping track of your units, you can see grams of aluminum cancel, moles of aluminum cancel. We are in the units of moles of aluminum oxide, but we need to get to grams, so therefore we need to calculate the molar mass of aluminum oxide, which is 2 aluminum, 3 oxygens, and that is a total of 101.96 grams per mole. Okay, check my units. Okay, I am now in the units of grams of aluminum oxide. So if I start off with 10.25 grams of aluminum, and assuming I have a sufficient amount of iron 2 oxide, I will react, and make 19.37 grams of aluminum oxide, 19.37 of aluminum oxide would be generated. Okay. This flow chart puts it all together for you. Okay. Now recall the bottom flow chart when we were dealing with STP, standard temperature and pressure. Okay. And so to get from point A to point B, regardless of, and that means generally any point in the corner most of the time, you know, if I want to get from grams to grams of something else, grams are given of some compound, looking for grams that some chemical, I cannot go directly at all grams to grams. I have to go through moles. So I need the molar mass of what I'm given, okay, which will give me the number of moles. And then this mole ratio comes from the balanced chemical equation, which would then give me the moles that I'm looking for. And then its molar mass will get me the grams that I'm looking for, okay? And I can go this direction, go like this in both directions. You're not limited to only one direction, okay? I could be looking for grams. If I need to make an X amount of something, I work it backwards to figure out how much I need to begin with. Right. Now, only at STP, okay, I can utilize that relationship of 22.4 liters per mole. And so I could go from grams given upper left corner to volume, okay? Look at the volume. If one of the products is a gas. So if I'm right here in moles finding, I can go in 2 directions and go up to get that value in grams, or I can go down to figure out that volume in liters. So this flow chart, study it, use it, because that really breaks it down for you to help you with the problems of when you look at it, you know, sometimes the problems are worded so they seem very, very difficult. And yeah, given this is the first time you've probably seen them, that's understandable. But you know, with any problem, I guarantee you break it down into steps, baby steps, break it down, you'll get to the answer, okay? All right. Eventually, the more problems you do, it just like anything else, you know, it gets better. You recognize things and you can do these calculations much quicker. All right. Now, what we have here is a written problem where they are telling you to write and balance the reaction of hydrochloric acid, okay, in solid cobalt. Okay. And so here we go. We got HCl, cobalt. So we got to write this reaction first. Now, additionally, cobalt is not one of the sweet 16 metals. Remember we talked about those with a constant oxidation state? So we have to tell you what the oxidation state is, especially in this scenario. So in this case, cobalt, when it undergoes reaction, will be changed to a +2 oxidation number. So let's write down the reaction. We have cobalt plus HCl. Cobalt's a solid, and HCl already given is an aqueous. Now, if you remember from the activity series, the atoms, the elements or metals that were in bold, those are very reactive and reactive with water. And then I said, okay, the ones that start off with magnesium, they're not in bold, and go all the way up to lead, right before hydrogen. Those will react, but they require a little more vigorous conditions, and they require an acid. This is one of them. This is a single replacement reaction. The cobalt's going to replace the hydrogen. Hydrogen, this is you'll see that cobalt's more reactive than hydrogen, and cobalt is not in the ionic form, so therefore cobalt will separate or replace the hydrogen, which right now is in ionic form, H+, gets converted to elemental form H2 as hydrogen gas. So we got hydrogen gas being generated. And cobalt, we've been told, is a +2 from the problem. And we know the chlorides are -1. So like I stated before, write them in ion form first before you put them together. You can see that we need 2 chlorides per 1 cobalt. So our formula is CoCl2. That's cobalt 2 chloride. Okay. Now, with respect to its physical state, well, if you look at the solubility rules for chlorides, this particular chloride is soluble. There's only 3 examples of halides that are insoluble: lead, mercury, and silver. Okay, so cobalt, this makes it soluble. Let's balance it. I got 2 hydrogens. What if I put a 2 in front of HCl? That balances my hydrogens, and lo and behold, it does balance my Cl, my chlorides. Okay, so they're happy. We got 1 cobalt. Everybody's happy. Okay. Now let's write the reaction. There it is. Okay. So now we have 2 HCl plus cobalt gives us cobalt 2 chloride plus hydrogen gas. Now questions could be asked. It says, how many liters at STP? That's good. STP tells us that we can utilize 22.4 liters per mole. Okay. So how many liters of gas? Obviously, the only gas we got here is hydrogen gas. So we want to know how many liters will form if 5 grams of cobalt reacted. So our interest is only simply between the cobalt and the hydrogen gas. We don't care about the other species. Okay. All right. So step number 1. We got 5 grams of cobalt, okay? And then I'm going to need a conversion to moles. And then from moles, guess what? STP, where at STP, I can convert directly to volume, liters. So I need 2 conversion factors here. And there's 5.0 grams of cobalt. Our first one is the atomic weight, obviously, because we want to convert the grams to moles. Remember, we're going to get 2 moles. Everything's going to go to moles. And then the stoichiometric relationship between hydrogen and cobalt, which is a 1-to-1. And since we are at STP, since this will put us in moles, we just one more factor that would give us the volume. So notice our units, keep track of your units, they're canceling out, all right, leaving us with units of liters. And this is what they're asking for. So now you just plug that number in your calculator and you should come up with 1.90 liters of hydrogen gas. Okay. All right, so what if 2.374 liters of hydrogen gas is formed? Question is how many, let me clear my mess up here. How many grams of HCl reacted? So we're still dealing with the gas, okay? If we have 2.374 liters of gas, how much HCl reacted? Question, how much HCl in grams reacted? That being said, I'm going to need the molar mass for HCl. Okay. All right, so let's set it up. Write down where we're given. Okay, that STP, being STP puts us into moles of gas, hydrogen gas. Okay, the mole ratio between HCl and H2 is a 2-to-1. And the molar mass of hydrochloric acid is 36.46 grams. Check your units. Okay, liters cancel, moles of HCl cancel, leaving us with grams of HCl. We are where we need to be. Okay, and plug the number in the calculator. You should have 7.72 grams of hydrochloric acid. Okay. If you started off with 2.374 liters of hydrogen gas. So if you, not, I shouldn't say start off, if you need to make 2.374 liters of hydrogen gas, you need to begin with, at the minimum, 7.72 grams of hydrochloric acid. Okay, here we have what reaction, again, given words, and you're asked to convert that into a chemical reaction. We got hydrochloric acid, which is in the gas phase, reacts with oxygen gas to produce chlorine gas, very nasty gas, and water vapor, which is in the gas phase. And so we have the chemical reaction written here, 4HCl, 1O2, reacts to give you 2 Cls and 2 H2Os. Everybody here is in the gas phase, okay? So we're given 3.00 liters of oxygen gas. All right, so we're going to convert that to moles like we've been doing, because we are at STP, we can utilize that relationship there. And then the mole ratio is a 2-to-1 with respect to chlorine and oxygen. And then that gives us moles of chlorine. So we're going to get back 2 liters of chlorine. And sure enough, we do the math. Guess what? We end up with 6 liters of HCl. Now, does anybody see something here where the conversion factors are mole ratios that we can simplify? Is there anything there you can see we can simplify? Anything in here? Well, look at this, look at that, look at this. Do they not cancel each other out? Okay. And the answer is yes. Okay. Point being, if I'm on gas all the way around and I am in STP, these guys here, I don't really need them. They're going to cancel out anyway. So the only thing I need really is the mole ratio between whichever 2 species I'm working with here. And this is between chlorine and oxygen in this example. Okay. But only if you are at STP. If the question was how many grams I needed, obviously the last conversion factor here would be the atomic weight or the molar mass of chlorine gas, right? Which would be at 70.9 grams per mole, and that would have given us the amount in grams. But they're asking for volume here. All right. Hopefully you see that. try these at home. If you have a challenge of it, we can work on it next time we meet. The question here says carbon reacts with oxygen gas to form carbon monoxide. Okay. And then once you got the equation written down, the question is how many liters of carbon monoxide at STP can be made from 15 grams of carbon? Okay. Second question, how many liters of carbon monoxide at STP can be made from 20 liters of oxygen gas? And you should come up with 28 liters of carbon monoxide and 40 liters of carbon monoxide respectively. The problem shown there, but don't look at it, just see if you can come up with it. 28 and 40 for question 1 and 2. See if you can come up with it. Okay. Well, let's kind of summarize a little bit. All right, we started off a while back. We got into the elements. We talked about the elements, how they're put together, electrons, and how they're put in energy levels, and how the driving force is to get the octet, either by losing or gaining electrons. And then from that, we create ions, either positive or negative ions, cations or anions. And then from there, we're able to put those anions or cations and anions together to form ionic compounds. And then we start taking ionic compounds and reacting with other ionic compounds to form new products, okay? So some of those ionic compounds come in the single replacement reaction, double replacement reaction, etc. Some of the covalent compounds, we did a combustion reaction, for example, to demonstrate that. But either way, the fact is that we started with elements, and then with those elements, we created compounds, which then react with other compounds. Then we start talking about how to balance these reactions, okay? Once we learn about the 6 different types, and then we learn how to recognize them, or talked about them at least, then we talked about balancing them, okay? And from these balanced chemical reactions, we get these stoichiometric relationships or ratios between reactants and products, okay? Which then allows us to do calculations of either the reactants or the products that are based on the ratios of the balanced chemical equation. And we can give various values in terms of either moles, grams, or if we are at STP in terms of liter or volume, okay? And this flow chart, I really would use it quite often to become familiar with it. This will kind of help you get you through the forest, if you will, of these calculations. But you're going to see that, once you do a couple and you become familiar, you just gain more confidence. I find that when it comes to working these problems, sometimes it's just a matter of confidence of being sure of what you are doing and setting that up. And one thing I can state is if you set them up with the units and you follow through and you're checking your units, making sure things cancel out where they should be, hopefully you shouldn't have a problem, okay? But if you do, I'm going to email away. Don't forget the Dana, Dr. Dana and Dr. Kim, who are giving weekly work problem sessions. Feel free to jump in there. Email me, okay, we can work through the problems if you need any assistance. So with that in mind, ladies and gentlemen, congratulations. You got 2 more chapters to go. I believe this is week 11, the end of week 11. So we really have, 5 more? And we only have 2 more chapters. So we're probably going to end up with